Kanji character recognition. The purpose of this demonstration is to illustrate the performance and power consumption differences between executing a neural network in software versus executing it in hardware on CogniMem Technology's CM1K chip. This demonstration takes part in two steps. The first time I run the application, I will do it without connecting our V1KU camera, which has the CM1K chip inside. This will cause the application to process the bitmap in simulation mode, which is a software simulation of the CM1K. The same steps will be performed a second time with the camera connected to the PC, which will cause the application to process the bitmap in the CM1K chip. I will now perform the first part of the demonstration. When the application is first loaded without a camera connected, it will run in simulation mode. I am loading a bitmap consisting of 8 rows and 15 columns of kanji characters for a total of 120 distinct kanji characters. You can see that while the knowledge base is empty, there are 0 neurons committed. Next, I will load an existing knowledge base consisting of 3 different perspectives of the 120 kanji characters found within the bitmap for a total of 360 neurons. I will select the Box Objects option, which will outline each region where a kanji character is recognized on the bitmap. I have the clock window open so that I can track the amount of time it takes to perform the task. I also opened the Task Manager window so that I can see the CPU utilization during the recognition process. The next step is to survey the image. This process cuts the bitmap into 16 by 16 regions of interest, takes each region of interest and feeds it to the neural network for comparison against each of the 360 models stored within the knowledge base, looking for a match. I am now going to survey the image. The actual time it takes to process the entire bitmap is hardware dependent. Before I start the process, note the start time and the average CPU utilization. I can tell that the process is complete because the application has highlighted each recognized character with a colored square. I will now perform the same process a second time. First, I will close the application, connect the V1KU camera, and relaunch the application. When the application is first loaded, it will connect to the camera automatically. I know if the camera is connected because I will not see the simulation mode dialog box. You can see that while the knowledge base is empty, there are 0 neurons committed. I am reloading the same kanji character bitmap and the same knowledge base of 360 examples, only this time the knowledge base will be loaded into the CM1K instead of into software. The next step is to survey the image again. Before I start the process, note the start time and the average CPU utilization. I am now going to survey the image. Since the processing will be performed by the CM1K chip, the actual time taken is not dependent on the PC, and you will see that the CPU utilization does not change dramatically. Each 16 by 16 region of interest loaded into the CM1K will have a latency of only 10 microseconds per recognition cycle, despite the fact that there are 360 models to compare it to. I can tell that the process is complete because the application has highlighted each recognized character with a colored square. As you will remember, during the first part of the demonstration, the CPU, a quad-core 2 GHz processor, averaged 13% CPU utilization, and the process took over 3 minutes, approximately 200 seconds. Given this data, we can calculate the approximate power consumption of 45 watts over a period of 200 seconds. Now, compare this to the second part of the demonstration when the CPU was idle, with the CM1K power consumption of 300 milliwatts over a period of only 6 seconds. This demonstration proves that the CM1K chip excels at pattern recognition with speeds over 30 times faster than a CPU and is nearly 5,000 times more power efficient than using a CPU when performing this type of task.